In this video, we are going to do an introduction to chemistry and start discussing the topics in Chapter 2, which include the definition of chemistry and how to do measurements. The first topic that we're going to be discussing, as you can see, is scientific notation. Scientific notation is a method to express very large numbers or very small numbers. And it is because we are going to utilize them in scientific calculations. To give you guys examples of very large numbers in chemistry or very small numbers, let's look at the examples that we have in the following slide. An example of a very large number can be the temperature of the core of the sun, which is 28,080,000 degrees Fahrenheit. As you can see, that number is very large because it has a lot of trailing zeros, okay? So zeros that are towards the end of the numerical value. On the other hand, to look at a number that is very small, we have the mass of an average human cell. When it comes to that, as you can see, the value is 0.000000000001 kilograms. As you can see in this value, the number is very small because we have a written decimal place followed by a whole bunch of zeros, and then we have a non-zero digit. So when it comes to scientific notation, this is a way in which we can write these numbers in a notation that then it can be utilized in scientific calculations. So as you can see, we have on the left of the slide the guide to writing numbers in scientific notation. Step 1 is going to be move the decimal point that is present or implied to obtain a coefficient, meaning a value that is at least 1 but less than 10. Step 2 is express the number of places moved as a power of 10. What does that mean? That coefficient we are going to write as a product of the coefficient multiplied by that power 10. Let's look at specific examples. So as you can see in this slide, we have for a large number the value 2,400. The value 2,400 does not have a decimal place written, but it does have one that is implied. And that decimal place, as you can see, is specifically at the end of the value. Again, rule number 1 says that we're going to move that value, that decimal place, three times. Let me just erase it and get started. We're going to move that decimal place 1, 2, 3 times because we need a coefficient that is at least 1 but less than 10. So when we move this decimal place from right to left, okay, 3 places, that means that our exponent is going to be positive. Again, when we move that decimal place from right to left, our exponent is going to be positive. What about if we have a small number? As you can see in the bottom, we have a small number. As I explained previously, this is going to be a number in which we have a written decimal place, and after the decimal place we have zeros, and then after that we have digits that are not zero. So as you can see, an example of a small number is going to be 0.00086. So what do we do when we have a number like that? Well, we are going to again move that decimal place. In this case, 4 times. 1, 2, 3, 4. Because remember that we need to convert this number to a coefficient that is going to be at least 1 but less than 10. Then we're going to write it as a product of that power 10. And remember, in this case, we move our decimal place from left to right. And because we move it from left to right, that's why this value is going to be negative. So now here, this is problems from the worksheet that we have. I'm going to do for you guys just letters A, C, and E. Okay, so when it comes to taking these measurements and putting them in scientific notation, we're going to follow the instructions that were given in the previous slide. So when it comes to this, as you can see, letter A, we are going to have a number that is very small. So we're going to be moving that decimal place from left to right. And in this instance, it's going to be 1, 2, 3, 4, 5, 6. We move it 6 places from left to right because we want a coefficient that is at least 1 and less than 10. So that means that when we change this measurement in scientific notation, it's going to be 1.8 times 10 to the negative 6. And we're also going to include the unit for measurement, which is the letter M, which stands for meters. In the next value, we do not have a written decimal place, but there is one that is implied, and it is at the end of the digit. And in this case, in order to make that coefficient be at least 1 and less than 10, we're going to move 1 time from right to left. So that means that for this value, the final answer is going to be 6 times 10 to the 1, and then we're going to put the letter S for second. On letter E, as you can see, that numerical value already is in scientific notation. So how do we write it at the end of the day in scientific notation? Well, we write the value, 6.7, and then the product of the power 10 is going to be times 10 to the 0, because 10 to the 0 equals 1. And then we're going to put the letter G. And this is how we convert things from regular notation to scientific notation. Now, the next topic that we're going to cover is going to be the units of measurement. A measurement is a defined, is a definite magnitude of quantity, capacity, or dimension adopted by a convention or by law. That is just the basic definition. So understand that measurements are going to be used by scientists in the metric system, and there's also a modification that has been adopted that is called the International System of Units, in other words, the SI system. And again, these are standards that are utilized worldwide. In table 2.1 in your textbook, as you can see, we have a selected number of units of measurements and their abbreviations for the metric system and the SI system. Be sure that you know which one corresponds to the metric system and the SI system. So as you can see, the measurement for length in the metric system, we have the unit of meters, which has an abbreviation of M, and it is the same that we have in the SI system. When it comes to volume in the metric system, we have the unit of liters, while in the SI system, we have cubic meters. When it comes to mass, we have grams. As you can see, the abbreviation is the letter G, and in the SI system, we have kilograms, which the abbreviation is kg. Next, we have temperature, which in the metric system, the unit is degrees Celsius, while in the SI system, it is Kelvin, and it is a capital K. And lastly, we have for the measurement of time, both in the metric system and in the SI system, the unit of seconds, and the abbreviation is the letter S. Now, when it comes to units of measurements, as you can see in the following slide, we have an example of students that are sitting in the student unit at Palomar College. Again, the basic definition of a measurement is going to be a definite magnitude of quantity, capacity of or dimension adopted by a convention or by law. So, if you take a minute and you look at this image, you can derive a few measurements in the system. Just to list a few, some can include the time of day, the volume in the students' drinks. And lastly, we can even say the length of the table. I imagine that there's other ones that you can imagine, but I'm just listing these few. Understand that units of measurements are all around us, and we use them in everyday life, and sometimes we don't even realize it. Now, in addition to measurements, now we are going to be learning how to do measurements, and after that we're going to have a discussion on significant numbers. Now, as you can see, when we are measuring a number, these measured numbers are going to be obtained when you measure a quantity, such as height, weight, or temperature. When you write a measured number, understand that there's going to be different numerical values that must be present in this measured number. Okay, as you can see, we are going to be writing first what we can observe, those numerical values that are in the marked lines, and those are known as known digits. Then we're going to write an estimated value, which is the number that we're going to be estimating that is going to be in between the lines. And understand that this estimated value is going to be the last number that we're going to write in that measured number. So let's take, for example, I'm going to zoom in into the slide. Let's take, for example, this object that we have in the ruler in the bottom of the slide. As you can see, this is a drawing of a pencil, and we have a specific ruler that is going to give us a measurement in the unit of centimeters. So the abbreviation of centimeters is cm. So remember, when we're writing a measurement, we're going to have known digits, followed by an estimated digit, followed by the unit. So going back to our example, in this case, our unit is going to be centimeters, just because of the unit that is shown in the ruler. Now, the known digit in this case is going to be 10, because we can observe that our object is at least 10, but not quite 11. So if I write a dotted line from the tip of my object down to my ruler, okay, we can see that the known digit is going to be at least 10. And because it is not quite 11, we're going to include a decimal place, and we're going to write an estimate. When you're doing an estimated digit, all you have to do is envision in your head that there's going to be 10 tick marks, and I'm just going to randomly write them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 10th one is going to be the 11. So, as you can see, here we can say that this measurement specifically is going to be 10.8. You don't necessarily have to write the tick marks. You can do it estimating it just by visualizing it. I just wrote them in just to give you an example. So when we report this measurement, as you can see, your known digit is going to be the 10, because that's the marked line that we know that is present. Then we're going to have an estimated digit, which is our estimate that comes from these lines. In this case, we are assuming the 0.8. Okay, we're estimating the 0.8. And then remember to include the unit of measurement, that in this case is centimeters. So I will say that this object is 10.8 centimeters. Now, to do an example of how we do measurements, remember that the way that we report a measure number has to do with the instrument that we utilize for the measurement itself. As you can see in the slide, I have three objects. I'm going to utilize the rope as an example. Let's say that for the rope specifically, I utilize the top ruler in order to measure its length. So if I select my object and I move it to my ruler, and again, this is just to give you guys an example. So I can say here that this object, if I do the same exercise in which I write the dotted line, it is around here. Utilizing that top ruler, I will say that my measurement utilizing that top ruler is going to be, let's say, 6.8 centimeters. Again, when it comes to this, remember that 6 is going to be your known digit. 8 is going to be your estimated digit. So that's where that comes from. Let me just erase those markings. Then if I take the same object and I use a different ruler, okay, let's say that I move it to the bottom ruler, and I take this measurement, as you can see, the bottom ruler actually has different tick marks, meaning that it has that first decimal place written in the instrument. What does this mean? That we have to take that into consideration as a known digit. So when it comes to this, if I'm utilizing the bottom ruler to measure the same object, then I'm going to say, well, I know that it is at least 6, not quite 7, and it still looks like it's 6.8. But in the bottom ruler, we're going to say that this is 6.81 or even 6.80 centimeters, because in this instance, your known digits, and I'm just going to highlight them in yellow, are going to be the digit 6 and then this area, which is at least 6.8, and then my estimated digit is going to be that second decimal place. So understand that when we're doing measurements, we are going to be making measurements based on the instrument given. And why is that? Well, because when we're doing measurements in the laboratory, understand that the instruments that we utilize are going to have different resolution, precision, and different significant figures. So the definition of resolution and precision are the following. As you can see, the resolution is going to be the quality to which an instrument can be read, while precision is going to be the quality to which an instrument can be read repeatably and reliably. So here we have two common instruments that we utilize in the laboratory in order to measure mass. They are measuring the mass of the same object. And in this case, that object is going to be that silver standard that I'm going to be highlighting in orange. So this that I just highlighted in orange to make it more visible. Okay, so you're utilizing two different instruments to take the measurement of mass for the same standard. Now, as you can see, these two instruments at this moment, we cannot tell from each other, if one is more precise than the other. The only thing that we can say is that the analytical balance, this instrument that is utilized for mass, has a better resolution compared to the top loading balance. And you may ask yourself, why is that? Well, because as you can see in the analytical balance, this little standard, this metal piece has better resolution in terms of we can see more digits in the reading of the mass for this object. Okay. Now, if we take the same object, and as you can see, we put it in a top loading balance, because we can only see in the display 3 digits, that means that the top loading balance has a worst resolution Again, for the measurement of mass, when compared to an analytical balance. And again, this difference in resolution between these two instruments for mass that we commonly use in the laboratory has to do with the numbers that we can the numbers that display in the screen when you are obtaining the measurement of mass. The precision of each instrument at this moment cannot be addressed because we are not performing an experiment in which we are taking the mass over and over on each instrument in order to study that. So the only commentary that we can have from these observations is that analytical balances have a better resolution because we have more numbers on the display when compared to the top loading balance.